story today is to look at the two nationalities, the French Lagrange, which we introduced in the last lecture that I've got stacked up on the final screen there, and the Hamilton, the Irish approach to mechanics. And the idea of doing that, the way we're going to do it is to make it clear that one of them is covariant and the other is contravariant. But of course, whenever you write an expression using this fancy GCC technology, you're actually writing an equation that's invariant to choice of coordinates. So when you, for example, write the Lagrangian the way we did, using a metric, we use covariant metric, but we deal with velocity, combinations of velocity with those coefficients. So it's both covariant and contravariant, it's invariant. The Hamiltonian that we're going to develop today using this GCC, same deal, except now we find a covariant thing here, that's the momentum, and we use a contravariant metric. Now just to refresh you on the wall there, refresh your memory a little bit, on the wall here we have the covariant metric defined by the dot product of covariant unitary vectors. That's the one at the top with the index down, and then the contras with their knives up in the air. The contra is a gradient. That's the vector is up in the air. It's normal to the surface, hypersurface, whereas these are along the coordinate line, and therefore covariant is the name that goes with them. The product of the two covariants or the two contravariants gives the metric tensor that, as I say, is very important in our physics of gravity, but we're going to make it part of our mechanics. Slight variation, which I'll talk about today, and that is that the mass of the object is included. So, just to remind you, these formulas here are here. The orthonormality relation is here. It won't be until Unit 3 that we get into the covariant derivative. That's a fancy derivative that lets you take account of the curvature of the whatever mechanical system you're talking about. Okay, the main thing I want to get across today is the advantages and disadvantages of each of these. There's no single Swiss Army knife for any physics that I know of, and mechanics is no exception. Sometimes it's really a good idea to use a Lagrangian. I think we made a pretty good case for it by doing the equations for the, well, Coriolis motion, but the hurricane equation, I call it, which is the one that showed up down there. So Lagrange has a very quick way to get you to the equations of motion and the physics that goes with it. Hamiltonian and Hamilton equations, not so much, but they have other advantages, and the other advantages are associated with symmetry. The Hamiltonian, very often, in the cases that we're going to be very clear about today, is conserved. The Lagrangian, you see, has underlying in quantum mechanics the phase. Phase is not conserved. Phase is going like mad. That's the heartbeat, I call, of matter, mc squared over h bar, really high. And so it's not conserved. That's not what it does. And so you can't expect the Lagrangian equation always to give you the conservation laws that you need. Hamiltonian, much better at that. And also there's this business of effective potentials. If there's one thing to learn from classical mechanics that everybody teaches, it's that. And so we'll be going over that using two examples, inside the Earth oscillator, outside the Earth Coulomb. We'll see simulations of those with the emphasis on what an effective potential is. So that's the main lesson that I want to get across today. Phase plots are important too. We'll get a little bit into that. as we go along here. Okay, so we've already, just to review things, had differential relations that we eked out of the geometry being on the right-hand screen there, and the equations that go with them for the Lagrangian and the Hamiltonian were in this, on this page in lecture 8, and again in lecture 9. So we're going to be doing more algebraic approach to all of this, but remember, geometry underlies that, so it's worth keeping that in mind. Okay, anything else I need to say about this? The force definition and the momentum definition, those are covariant quantities, indexed down. The covariant G that goes with contravariant velocity, that's Lagrange's. That would be Lagrange's way of doing things. Now this GCC is developed by a completely different part of the world. The German approach, the Riemann and Gauss are responsible for that. So I hadn't quite caught up with Lagrange, and so Lagrange didn't take advantage of that to his disadvantage. Okay, now Hamilton, as I say, is the topic of today compared to that, and we will be comparing them. So let's go ahead and get started with that idea. This being the Lagrange thing that we developed before, and now we're going to do the Hamilton discussion. So how do you derive algebraically all of this stuff that we've talked about that the Hamiltonian does covariantly or contravariant, depending on how you look at it? We need to see that. This is, I'm going to keep all these three screens synchronized for this part where we do the nasty little algebra that goes into the development of Hamilton's equations. It's actually not so nasty. It's kind of tricky, but it's quite beautiful as an algebraic thing. Of course, the geometry makes it more beautiful. Now, here we're talking about the total time derivative of the Lagrangian. Remember, I say that's associated with, in quantum mechanics, the underlying phase of matter, matter waves. But here, these people who developed all this didn't have any idea about that until very late in their careers. The idea is to use chain rule to write that thing as a function of q as coordinate, queer coordinate, and the queer velocity, q dot, and possibly, there's an explicit time dependence. Somebody's mucking with the apparatus that is this mechanical system. So in addition to these two terms involving the time derivative of the coordinate, that's a velocity, and then the time derivative of the generalized velocity, that's an acceleration, a queer acceleration. We need to advance this to the point where you include time as well. Now, the chain rule factor here just becomes 1, so you end up here with a partial derivative of the L. That is the part that you would get only if there was an explicit time dependence going on here, which I'll make a big fuss about very shortly here. So, looking at this, and that's one way to think about it, an explicit time dependence is somebody messing around with the experiment in the middle of the flying of the mechanical system. And here I'm reducing class size. Okay, something I had to try to do at the beginning of this class as we try to figure out where to put everybody. Okay, and it's the idea of making a small class is in this cartoonish way of imagining explicit time dependence. So you're like a mad scientist when you're playing with this term right here. You're catching the thing mid-flight and changing something. So this is what we have set up here for getting the algebra for the Hamiltonian. Okay, the first step in this is to use Lagrange's equations. We're going to use Lagrange to tell us what those coefficients are in terms of momentum. And the idea, as you have already been told many times here, is that Hamilton wants to work with momentum, not velocity. So we're going to have not just the momentum given from Lagrange's equations, but we have the other Lagrange equation here where you take the dot off of the Q and put it on the P, right? Easy way to remember the Lagrange equations. But here we use them in order and replace this coefficient of the chain rule with the P and the P dot. First the P dot and then the P. Okay. So that's it. That's giving us now the total time derivative of our Lagrangian. And get it up here too. Okay. Now, putting that together, putting those two first two terms there together, just using the product rule, that is, the derivative of u v dot becomes u dot derivative of v, that's an acceleration, and then u v dv dot, okay, that's a derivative of an acceleration again. Now that's a jerk, actually, right there. In any case, you can rewrite these two terms just as a total time derivative of that product. Now that's something we're going to call the action, or it has a bunch of terms that make up, we call it reduced action later on. So there's an interesting piece of physics showing up right there, and that equation gets flipped, and I've got the expression for Hamiltonian. So that's all there is to the connection between, algebraic connection between these two famous mechanical devices, I might say. But this one right here is got some advantages over this one. But this is a quick and dirty one, and it's the one that you get taught in almost every mechanics class first, and then maybe not at all. They get doing much with the Hamiltonian. Quantum mechanics, it's the whole story. So when we make that connection, we're going to have to talk some more. But in any case, the idea is that this total time derivative of this quantity right here, that is the difference between the Lagrangian action and just the raw momentum times velocity action, that difference is the Hamiltonian. And we've got a lot to say about that as we try to make a connection with quantum mechanics. But let's finish the algebra here, because it is rather striking. What a weird equation. The total time derivative of this Irish thing is minus the partial derivative of this French thing, the Lagrangian. That's kind of weird. That's that's bizarre. Now, you should be aware that these equations are all up on the wall there, and we've just gone through the center portion of the main equation set there. So we're making progress in this course here, and I hope to continue doing that. Now, the first derivative, this equation right here, Hamiltonian equal PV minus L, P dot V minus L. We've seen that before. We did it more or less hand waving, but was the geometry behind that was what I was showing on the slides just coming in today. So there it is. That's the Legendre transformation. And of course, it could go either way. I can get the Hamiltonian from the Lagrangian by doing that, or I can get the Lagrangian from the Hamiltonian by switching those two, right? So this is a transformation very obviously going both ways. easily. Okay? Now, what else needs to be said here? The explicit dependencies need to be pointed out. First of all, we've said this many times, explicit dependence of L with respect to the momentum. Triple equal sign 0, identical 0, okay? But a lot of argument was needed to get this, right? This is not something that you just say and then walk away from it. We had to show that the tangents going from secants to actually touching the extrema that required this, and then we did it with the Hamiltonian, okay? So that's the key thing here in understanding the actual Hamilton equations of motion, which are going to be in the lower part of this in just a second here. Okay. Now, what this tells you is that the partial derivative of the Hamiltonian with respect to momentum, okay? In other words, if this is a Hamiltonian, I go here and do a partial with respect to momentum. Well, right away I see partial P with respect to P, and that's true for each component, okay? And this is the case where I've repeated indices on both sides of the equation, so I'm not summing anything at this particular stage. I am here, but when I do this partial, well, it's on both sides, so I'm going to get just plain Q dot M is the partial of H with respect to PM. And that is Hamilton's first equation. Writing it over here. Hamilton's first generalized curvilinear coordinate equation is that guy right there. Let's get it down here as well. Okay? Well, we still go back and what's the partial of H with respect to the coordinates? That's the other thing that we're going to be needing here. And I note, and these are sort of very trivial relationships here, for mechanics, the idea that momentum is independent of the coordinates, so are the velocities. Each of the velocities are independent of the coordinates. And so this partial dependency here is identically 0, both of them. And that means when I go through and take a partial of this equation with respect to a coordinate, I get 0 times 0 is really trying to tell me something right here. This is 0, and then I have minus the partial derivative of the Lagrangian with respect to a coordinate is what's left. Okay? So that is what gives you this relationship right here, but that is Hamilton's second equation. The one that we couldn't derive because we had no dependency of the Hamiltonian, the energy expression, or the Lagrangian expression. We had no dependency of that on space when we were doing the Superball things, or the very first day, SUV versus VW, right? The idea was that the actual positions of those cars gave no force dependency until they met, and just very briefly then there was lots of dependency of the force on position as they went like that, and maybe popped back if it was time reversible, or just crumbled. Okay, so there was only that very brief dependency on space. Otherwise, we were idealizing it. No friction, no wind, no air resistance, no forces at all, right, on that first do of mechanics. Well, here we're finally remedying that. Those are the equations of motion that Hamilton is credited with developing. Now there's lots of other people that developed that sort of at the same time. He's the one who gets the credit. That's the way it works in science. You know, somehow you work your way up through the politics and get your name on it. But Hamilton is a really bright guy and certainly deserves credit for this development. Okay, so that's what we're dealing with. The idea is to compare this with the Lagrangian way of doing things. You wouldn't think you'd need two complete ways to do things here. But I do want to point out that this is one of Hamilton's equations, a weird one. Very peculiar relationship involving the partial of L with respect to time, explicit time dependence of L. Is there a mad scientist running the changing parameters in the experiment? If there is, then the partial derivative of L with respect to time will be by clear analogy non-zero. But if you don't, if you leave your hands off of a mechanical thing, make an autonomous system that isn't being touched or messed with by any outside influences, you are then guaranteed that the total time derivative of the Hamiltonian will be zero as this is, exactly. So that's neat. That gives you an indication of what's happening to your total energy. That's what this is going to be. We have to prove that yet. But that's really a key result there. That I pause and let you think about it a bit. It's really worth seeing this and thinking about it. This is a very interesting way of doing the calculus of mechanics. Now, we have to pull this all apart and make equations that just involve velocities or momenta or whatever. Here's one involving momentum, and we're going to be using these covariant metric definitions of the Lagrangian and P. Okay, here's the covariant metric that we use, and the idea is to get the Hamiltonian written like that as well. So the actual practical applications of all of this beautiful stuff is yet to come here. Okay, let's get that started. If there are no questions. Is this making sense so far, just as a logical piece of algebraic intricacy? Now, a combination of these is really what you need. Legendre transformation is very much a part of making the jump to Hamiltonian. Lagrangian, fairly easy to develop. Hamiltonian, not so easy, as you're going to see here. Okay. So I'm replacing the Lagrangian, and I'm pointing out it is a function of velocity. It's also a function of coordinates, but emphasizing its dependency that differs from that of the Hamiltonian. And so here sits L, and here sits, well, we've dressed this one up. We've shown what P really is. P, momentum, is the partial of L with respect to Q dot. That's Lagrange's first equation. And then we take the L and differentiate it with respect to the velocity, and reduces this quadratic form to a single linear equation involving the velocity, Q dot. Now let me get everything up to match here. Keep these things in sync as much as I can here. Go ahead on that one and this one. So here is what I call an illegal dependence equation for the Hamiltonian. Okay, sitting here with the velocities. That's not what it's supposed to be a function of, but that's what comes out numerically. This is something that's numerically correct. We're going to have to fix that, but right at this particular venture, it's not. Okay, so we take this inverse relationship of the velocity to the moon, just flip the equations by using the contravariant metric, applying that to P. Basically, that's all that's going on here, but I'm just solving the equation here that expresses the momentum the way it was in the developmental Lagrangian stuff, and getting the velocity as a function of momentum. So I can replace these velocities here with something that involves momentum. And that, the details are on the next page here, but this one is both formally, that is differentially, and numerically a correct equation. This one's true numerically, but misleading, because the important dependency of momentum is really key to using a Hamiltonian. Okay, I'm going to take that one down there up to this point. Here's the beginning of the details of doing the tensor algebra to show this. This is not trivial. It's easy, but not trivial. You have to get used to it a little bit. One of the things that's really key to all of this is that the covariant and contravariant metric matrix, the quadratic form elements, are symmetric. Okay. And we may notice this on the very first lecture when we talked about a mass matrix. And it only had diagonal terms, so it was symmetric by default. But in general, we're going to, all through the applications, make use of things that are like metric tensor, all the way up through mechanics of gravity, demand that. It's kind of like the demand that the quantum mechanics has for Hermitian operators, and the Hermitian Hamiltonian, but also other matrices that are involving things that are time reversible. They will be symmetric if they're real, Hermitian if they're complex. So here I'm just going through and I'm stuffing the Q dot into this equation right here and putting little helper lines. Remember I said that when you start to get algebra, it's a little bit more complicated like this is. It really helps to draw a little something between indices that are equal on one side of the equation and therefore being summed over however many degrees of freedom the system that you're dealing with has. So I've got a few of those in there. In here, when I take this thing aside and stuff that thing into here, thereby making it a little clearer where things is, because now there's a big space between that end and this end that have to be summed over the covariant, contravariant, and indices, and all the sum of whatever degree of the freedom number is. So here's our Hamiltonian, almost in the form that we're going to let. But you'll notice that what's happened here is when I put this thing, because we have a minus here times a minus here, and here's where the potential that in the Lagrangian had a minus sign in front of it, in the Hamiltonian it's got a plus sign. Big difference. Okay, that has to be in order for it to be a conserved quantity in the case of no explicit time dependence. Okay, so that's where we're headed here, is rewrite this thing in such a way that I can just collapse it to a contravariant metric and a covariant kinetic quantities, the covariant momenta are sitting there. So that's the result we have now. The thing that's a little weird here, and this is why this particular approach using GCC at this point is, maybe in question. We are dealing with a metric expression for kinetic energy. We're dealing with the square and some coefficients of that, a combination of products of velocities and eventually, and now, momenta. And we have to either have an M or an inverse M if I'm talking about a single particle in some weird coordinate system, and I am, I've got one mass here, and that's, this derivation is just for that one mass. The full derivation of Lagrangian and Hamiltonian, you see, is not in this review unit. I stuck this in here just to get you the simplest pathway to Lagrange and Hamilton mechanics for one mass. In crazy coordinate system, whatever. Well, not a crazy coordinate. We use the polar coordinates. That's what we're going to actually pull up in just a minute here. But be aware that Unit 2 and Unit 3 are devoted to doing the full job with masses connected and making a trebuchet machine, or you know, all kinds of weird mechanical devices that we'll you know, take looks at later on. But in any case, right now and later on, I will be calling this gamma Mn, and the gamma will be just full of mass dependency, depending on how many masses you have in there. They can all be different or all the same. But that is going to be the way we get to use the full power of the differential geometry of Gauss and Riemann in mechanics. And I think it's really a powerful addition to the way we do these things. In any case, this is the Hamiltonian that we have right now. It has a kinetic part, which is somewhat verbose, but it has a plus the potential. And that is our total energy. And that is formally and numerically correct, and that's what we're after. And if the polar coordinates for the Lagrangian is that, okay, well, it's got to figure, we have to know what GRR is and G phi. Remember, they are not so simple. They're written on that far screen down there. The coefficients for G, Mn is up at the top there. R, phi, R, and phi are the dot products of the unitary, and that's something I haven't mentioned yet, is they're called in all of the literature that I can find unitary vectors. They're not unit vectors, so they just put a ARY on that, unitary. They don't mean the unitary you have in quantum mechanics at all. It's a different definition entirely. So do not confuse the name unitary that's used for this stuff with the unitary and the quantum that goes between bras and cats and all that. So anyway, there's the Lagrangian. I'm going to get all this stuff in sync here. There's the Hamiltonian getting ready to come out there, but right now it's the Lagrangian in the polar coordinates using the metric that is up on the fourth screen, the very upper right hand corner there. And actually, I just noticed the matrix is hanging on the edge there. There's a list of the coefficients right there that we need for this. Okay, so maybe I'll put that in the center, back this one off, and that's what we're dealing with. Okay, so this is our Lagrangian, and then it's just a question of how you convert this to a Hamiltonian. We simply put in the inverse of the metric. That's really easy when it's diagonal, because this is an orthogonal coordinate system, so all we've got is RR and phi. We don't have R phi and phi R, okay? But anyway, we're going to be replacing that minus sign with a plus sign, and we're going to be using the contravariant metric. That's the only change that's in effect here for this. Okay? So there's the only weird term, remember? MR squared omega squared. That was the kinetic part with the rotational inertia. All right. So Hamiltonian comes out looking like that when you make that adjustment. Okay. So we end up here with one more step. That's the whole thing right there. I'll leave that there. Okay, So we've got the radial momentum squared, and we've got 1 over r squared, the angular momentum squared. And then we've got a plus sign on u instead of a minus sign. So there's a good chance to compare, in this simple coordinate system, polar coordinate system, the relationship between the Hamiltonian and the Lagrangian. Okay? All right. Now, how hard is it to take this thing and do all the stuff that we did on the screen, the fourth screen over there, with respect to equations for r dot, p dot, phi dot, and, well, just the equations of motion. That's stuff that came pretty easily here. Not so easy for this. Not so easy. And that's because it got these inverse, contravariant metric coefficients multiplying the momentum. So we're going to go ahead and get through that. Now, the main point of this is going to be that Hamilton's equations compared to Lagrangian's are more complicated, more algebra, even for this simple polar coordinate system. But I'll point out at the end that Hamilton's equations are in a Runge-Kutta formation. That is, they are set up for a workhorse for numerical simulation is fourth order RK, Runge-Kutta. Okay, there's some Indians involved in this, I think. Okay, and that is a powerful method for doing, well, all our simulations are basically Runge-Kutta. Maybe with adaptive step size for things like Coulomb, which we'll see today, where you really need to be careful as you go real close and get really high values for 1 over r, or 1 over r squared, depending on what you're dealing with. Okay, but Hamilton's set up to do that. Okay, much better, I think, than a Lagrangian. But you can do a Lagrangian too. I'm just making a case for Hamilton at this point, where he's beginning to look a little weak. All right. So let's look at the beginnings of that. The idea being that you need to take his first and second equations, and each one of these has to have something to do with momentum that has the radial component, and then the momentum that has the phi component, and that's going to be related to velocity of those two choices that we have for the two-dimensional single mass in a polar coordinate situation. Okay. Well, first part's pretty easy. Look up here at the h, I can take a partial derivative of p as good as anybody. What I'm noticing here, partial h with respect to pr, okay, this, let's see if I've got that, right here. This is the equation where r is our number 1 coordinate. So this is r dot, this is phi dot. I'm just writing down that first equation, and then the second equation is going to be done with the other parts of the component, angular and radial. Go ahead on that one. Let me keep up. There's the equations that each of those gives. So it's going to just be a matter of taking some partial derivatives for the first part of this. So when I look in there for the partial derivative of the Hamiltonian with respect to PR, it's pretty easy. I'm going to be getting a partial derivative of something squared, so it's 2 times, and then I'm going to get this into the first power, and that is going to give us this little deal right here. I've got this 1 over the mass, you see, so right away I'm seeing here PR divided by mass. Okay. At first maybe that looks a little awkward, but you'll see that it's not so bad. Okay, and same thing here. Now, the next step okay, I take a partial of the Hamiltonian with respect to p phi. It's a little more complicated now. I got a 1 over r squared here, but that's not anything but a factor. I again get the 2 canceling the 2, and get a nice relationship just involving the first power of phi. Now these are partials, so all the other terms that don't have dependency on p phi, they're not playing a role at all at this point. Go on to do it with the second equation of Hamilton. This one, gradient on the coordinate ellipse is equal to minus the p dot here. That's kind of, as I said, a little bit weird. But let's go ahead and do it on these sets here. Okay, and also while we're at it, notice that when we have to take a partial derivative with respect to the coordinate, angular coordinate, we're going to get something as well. Not as much of complexity as this one, though. This one is kind of weird. I've got a 1 over r squared here. Got to be careful to keep track of the extra r's that I'm going to be having here. The 2's cancel again, and I get a p squared, or r cubed. That's kind of weird. Now already you can see, just at this point, and we really haven't done anything but take partials, that this is more complicated than what we were doing with Lagrange, right? Okay? It gets worse. We go and we say, hey, don't I remember that PR is MR dot? Well, that's what I get from these two. Okay, so it gives me something that I have immediately, the very first upper left-hand corner of the Lagrange thing. But you want to check that out. This canonical momentum is a little weird, so we want to be careful about that. So that is part of this thing and this thing as well. Next step, okay, the p phi, all right? Where does that come in? P phi here is mr squared times that. Well, partial h with respect to p phi is phi dot. So that gives me this little guy right here. So we get p phi equal mr squared phi dot. That was a big accomplishment. We got in one step down there. Took a couple of steps to get it here. Okay? Well, it goes on. This one right here, okay, same thing. And now I'm looking to see relationships here now with the radial velocity and the angular parts. And I'm going to do it again over there. That one's not so bad. That one comes out something that you recognize immediately. You could have probably written that down first step. But this one in the middle is not so easy. Okay, so you see, here we're just talking about single mass and two-dimensional polar coordinates, and I already got boards full of equations, right? And a few steps where you can easily make arithmetic mistakes. I'm very careless, I think, with my calculations, so I have to go do these things 2 or 3 times to get them right. But this one right here is kind of a peculiar guy. So what we have to do is do an end run around this thing. We say we've got PR equal mr dot. That means if I take the time derivative of that and the mass doesn't change, that's it, goes without saying, I got a p dot r here equal mr dot dot. Okay, so I can immediately set that just because I have this one right here already in that form. I can get an equation for p dot r from that. But I have to use this guy right here. Okay, stick that guy in there. Okay, and end up with a p dot phi, and there are equations that we got, as I say, at the very bottom with one step in the Lagrangian development. So you can see there's a lot going on here. As I say, now compare it with the Lagrangian result. You can see that just for this very simplest thing, a single mass in 2 dimensions in polar coordinates, a lot more work than just going to Lagrangian. Okay, so 1 point for Lagrange, 0 points for Hamilton. In the secretarial work, you might say, because of this stuff. Okay, there's a thing we're comparing up here. All right. Now, just to pull something out for poor old Hamilton, he's feeling kind of bad. This guy's in Paris or beating his ass. What can we give him? Well, I can give him this. And this doesn't happen for half a century or more from when he lived. And that is that we have computers that can rip through something like that. That's the Runge-Kutta setup. Okay. So just equations involving the positions or whatever. If you've got first order differential equations set up in such a way that you've taken apart, obviously, some second order differential equations, or maybe higher orders are at work here. But in any case, we can rewrite this very nicely in terms of r dot, pr dot, phi dot, and p phi dot, and then presumably have equations immediately for each of those. We're in business. We can just work that, and this is the polar coordinate form right here. So I hold that up as something that we kind of do all the time in our business here. And you'll be seeing simulation that is actually using this. Okay, now something else. This is where Hamilton shines. This is where it really makes a big difference. And this is where we'll see the simulations that go with it. Both for oscillator, that's inside Earth, inside sophomore physics Earth, and while we're at it, we'll do the outside orbits as well. The hydrogen, kind of Hamilton mechanics that you would do if you're doing semi-classical mechanics of the hydrogen quantum mechanical problem. So that's very much in the offing here. Okay? And the reason it works is because of conservation. First of all, if h is not an explicit function of h, and this would be true for Lagrangian too, but here we get to make use of it. If in fact the second equation of Hamilton notices no explicit dependence in the angle phi, that means the thing has a cylindrical or even spherical symmetry, we're in zero land for the partial derivative that's causing us to have a complicated equation involving this Hamiltonian. So if h has no explicit dependence, it has symmetry. Symmetry, S-A-M-E-T-R-Y, okay? It's always the same in all different angles, okay? No partial derivative with respect to phi. I've got no change in the angular momentum, p phi. E sub phi is fixed, a constant. Now I use the atomic notation very often used for angular momentum, L. Now that comes from the letter L for Lagrange actually, but that's just a little bit of history. So what we can do here is go through and take the entire Hamiltonian, which has two kinetic variables and two angular variables. One of the angular variables out, so that makes one of the kinetic variables into a constant. And there's a name for that. That's called the effective potential. Now this is true not just for the Coulomb problem of the sophomore physics Earth outside, not just for that, but for any problem that only has a radial dependence. It doesn't matter what the radial dependence is. This is going to work. Okay. You're going to be able to take the real quote-unquote potential. You're going to be able to take that and add it to something that is involving the angular momentum constant and maybe some more functions of r, but that's it. That's going to be an entire effective one-dimensional potential. And there's a name for this. It's called the centrifugal barrier potential. It goes to the quantum mechanical scattering problem that came up after all of this stuff got used for quantum mechanics. So this is a real plus for using Hamiltonian, that you can do this fairly easily with some pretty complicated machines, like a trebuchet, which is what we'll be using in Unit 2 to develop the most complicated Lagrangian algebra that you could possibly have, and still be able to live through it in academic terms. So once you get this, you're then able to solve for the radial momentum. And as I said, this is true for any UR, not just the oscillator, which we'll treat, or the Coulomb, but you name it. Now, it may be quite pathological. You may get all sorts of very weird mechanical effects, quite beyond what the oscillator and the Coulomb think. So they have hidden symmetry that most of the functions of U, functions U of R, would not in general have. So it's quite easy then to go ahead and solve the momentum, how fast the thing is going in the radius as a function of the radius, its closed form. And not only that, but in this case, and it's pretty much true in cases related to this, you can integrate the results. Now, we won't be doing that until we're in the middle of Unit 2. And then I'll do both of these together, the Coulomb and the oscillator, right on top of each other, show the differences in each state. That's really fun. You see some very strange symmetries sort of popping out if you look for them carefully. But right now, I just want you to see that we have an integral here for a potential, and I'm thinking of the oscillator potential, kr squared, that has an integral that looks like that, and the Coulomb is kind of related to it in a funny way, but anyway, when you do this, when you reduce the thing using an effective potential and the Hamilton giving you some extra conserved things, that is beyond the energy which we